The last time we looked at the concept of reduction. Okay, so let me just quickly review what we mean by reduction. So reduction means this: given an efficient algorithm for problem pi 1. Okay, so you are given an efficient algorithm for problem pi 1, then using this we designed an efficient algorithm for a different problem. Okay, so we essentially showed that this implies that there exists an efficient algorithm for problem pi 2. Okay, so given that there exists an efficient algorithm for problem pi 1, this is one problem. We show that there is an efficient algorithm for problem pi 2. The way we do it is, imagine that this pi 1, somebody has coded pi 1, an algorithm for pi 1, and it exists in some library. Then we use this, okay, to design an algorithm for problem pi 2. So this algorithm that we design, it takes as input an input for problem pi 2, okay, it perhaps does something to this input, okay, and then calls this subroutine for an algorithm pi 1, maybe once, maybe twice, repeatedly, and at the end of this it outputs an answer, and this answer is for problem pi 2. So essentially we have solved problem pi 2 assuming that somebody has given us a solution for problem pi 1. The two problems we looked at last time was pi 1 was given a graph, okay, does that exist a perfect matching in the graph, okay, that was pi 1, and the algorithm we designed was given a graph, output a matching of maximum size, okay, that was pi 2, and we did in fact repeatedly call this pi 1 after modifying the input slightly. Okay, so why is this called a reduction? Okay, it's called reduction in the following sense, that you actually want to solve problem pi 2, and you have somehow reduced this problem to solving the problem pi 1, in the sense that if you can solve problem pi 1, you can solve problem pi 2. Okay, so you have reduced the problem pi 2 to a problem pi 1, and that's how the word reduction comes. But the essential method is this: given an efficient algorithm for one problem, find an efficient algorithm for another problem, okay, and you have to use the algorithm for the problem given to construct this efficient algorithm. Okay, so this was a concept of reduction. We will in fact see one more example of this very shortly. Okay, before we see an example, here is a word which seems a bit new, okay, which is efficient. Problems have been defined, we've seen many problems. Algorithms have been designed, we've seen many algorithms. But what does this efficient mean? Okay, so let me define what I mean by efficient. We had seen earlier a solution to one of these scheduling problems, okay, where the time taken was just too much. That was an inefficient algorithm. An efficient algorithm we would like to be something that on reasonable sized inputs finishes in reasonable amount of time. Okay, so let me tell you algorithms which are not efficient to start with. So these are usually brute force algorithms. Or not efficient. So what do you mean by brute force algorithms? Brute force algorithms are algorithms that that look at all possible solution sets. Okay, there may be many possible solutions given your input. There could be many possible solutions, and you want to pick one which is good or the best, right? So the brute force algorithm would look at all possible ways of doing this and pick the best one. For instance, if you want to look for a matching of maximum size, a brute force algorithm would look at all possible collections of edges, okay, all possible subsets of edges, then check whether each subset is a matching and also the size. And from these, from this you can certainly find out a matching or maximum size. But this algorithm just takes too much time, right? So if there are m edges, then you take 2 to the m, you have to look at 2 to the m subsets, and we've seen that this is just too much. Okay, so these usually search exhaustively through the entire solution space. Okay, and if the input is of length n, okay, that's the other sort of characteristics of these brute force algorithms. If input size is n, typical times taken by these brute force algorithms is 2 to the n, because they just look at all subsets. Okay, typical times are 2 to the n, and this is just too much. We saw that if you design such algorithms, you may get fired. Okay, so these are not the algorithms that we are looking for. These are not efficient. So what do I mean by? Okay, so by efficient, I mean that the running time of the algorithm is bounded by a polynomial in the input size. Okay, let me write this down. For us would mean this: the running time of the algorithm is bounded by a polynomial in the input size. Okay, so let me restate this again. What do I mean by polynomial? The running time which is bounded by, let's say, n to the constant. Okay, so let me just state this again, which means I'm just going to restate this. There exists a constant C such that the running time T of n is big O of n to the C, okay, where n is the input size. So this is what efficient for us will mean. Most of the algorithms we have studied so far are efficient in this respect. Okay, for instance, sorting you can do in n log n time. Okay, that's certainly bounded by a polynomial n squared. It's bounded by n squared. The other algorithms that you have studied in your divide and conquer or dynamic programming, they're all bounded by a polynomial in the input size, n squared, n cubed. Shortest paths, finding minimum spanning trees, almost any algorithm that you have studied so far. Okay, they're all, the running times are all bounded by a polynomial in the input size. Okay, and these are the algorithms you have studied so far are efficient. Why polynomial? Okay, why is this the notion of efficiency? I mean, why not some other function of n? Okay, so the reason is this: if you compare, okay, n to the c, so compare n to the c and let's say 2 to the n. So these are 2 to the n is what brute force algorithm would take, and n to the c is what our notion of efficiency will be. Okay. If you look at these two functions, then 2 to the n grows just much faster than n to the c. Okay, so even for inputs of size 1000, 1000 squared and 2 to the 1000 are just two different things. If you have something which is, let's say, n squared, okay, then if you program an algorithm which runs in time 1000 squared, that will take a few minutes to complete. If your algorithm takes time 2 to the 1000, well, it's not going to stop, at least in our lifetimes, maybe much more. Okay, so that's why this notion of efficiency has been, is prevalent. The other sort of reason is in practice, usually when a problem has an algorithm which runs in time polynomial in the input size, okay. So usually in practice, if there is a constant so that you can bound the running time by n to the c, this c happens to be very small, okay, 2 or 3. There are very few algorithms whose running times are more than n cubed, okay. If there is a polynomial time algorithm for the problem, which means the running time is bounded by a polynomial, then usually this polynomial is small, like n squared, n cubed log n, etc. Okay. So in practice, if there is such a c, usually c is less than or equal to 3. So that's why one uses this notion of efficiency, and this is a notion we'll use for the rest of this course. We said that if there is an efficient algorithm for problem pi 1, there is an efficient algorithm for problem pi 2. Okay, so let's again look at the matching example that we did. Okay, so pi 1. So we said that let's assume there is an efficient algorithm for perfect matching. Okay, so this we said implied an algorithm for finding the size of a maximum matching, and this implied an algorithm for finding a maximum matching. Okay, this is what we saw last time. Now, even though this algorithm is efficient, it's not necessary that when you do this transformation, the new algorithm is efficient. In this case, it actually is true. The reason is this algorithm is called at most n times. Okay, so if the running time were, let's say, n to the c, this was called at most n times. So the running time here is roughly n to the c plus 1. Okay, and this called this at most n times. So this turns out to be n to the c plus 2. Okay, so if there is a c, if there is a constant c, so that this running time is bounded by n to the c, there is some other c possibly. Okay, maybe c plus 2, maybe 2c, so that the new algorithm runs in time n to the c prime. Okay, so that's what I mean by saying that if there is an efficient algorithm for problem pi 1, there is an efficient algorithm for problem pi 2. Okay, for our next problem, I need to define a couple of terms. Okay, these are concepts of a Hamiltonian path and a Hamiltonian cycle. Some of you may have seen this before, but let me define this anyway. So a Hamiltonian path in a graph G is a path of length n minus 1, where n is the number of vertices. Okay, it's a path of length n minus 1 where n is the number of vertices. In other words, it's a path which spans all vertices. Okay, in other words, it is a path that contains all vertices. Okay. So, it must be a path in the graph and all vertices in the graph must be present. Clearly, the length is n minus 1. Okay. The number of edges which is a length is n minus 1. Okay. This is a Hamiltonian path. A Hamiltonian cycle is very similar. Okay. It's a cycle which spans all vertices. It's one single cycle which spans all vertices. Okay. So, let me write this down too. A Hamiltonian cycle in a graph is a cycle which spans all vertices. Okay. So, let's look at an example. So, okay. So, supposing this is a graph. Okay. Maybe let me add this too. Okay. Now, here is a Hamiltonian cycle in the graph. This, okay, this edge, that edge, this edge, that edge, this edge. Okay. So, this is a cycle which has all the vertices in the graph, right? And if I remove any one of these edges, it gives a Hamiltonian path in the graph. Okay. Any one of these edges in the Hamiltonian cycle, this gives a Hamiltonian path in the graph. So, if a graph has a Hamiltonian cycle, it has a Hamiltonian path. The reverse, of course, may not be true. Okay. So, for instance, if the graph is just a path, if the graph is this path, then it has a Hamiltonian path and it has no cycle. Okay, it does not have a Hamiltonian. So, now that we have defined these two terms, let us put them to use. So, we are talking of reductions, right. So, we are going to see how closely are these two problems that I am going to define right now related. Okay. One is the problem of finding Hamiltonian paths and the other is the problem of finding Hamiltonian cycle. Okay. So, the first problem is called Hamiltonian cycle, HC. It is this: input is a graph G. Okay. The question you ask, does G have a Hamiltonian cycle? Okay. Hamiltonian cycle. This is problem HC. Similarly, I have a problem HP, not to be confused with Hewlett-Packard. Okay. Input is a graph G. The question, does G have a Hamiltonian path? Okay. So, for this problem, you want an algorithm that says you feed in a graph G and this algorithm should say either yes, the graph has a Hamiltonian path, or it should say no, the graph does not have a Hamiltonian path. Okay, that is for this problem. For this problem, it should say yes if the graph has a Hamiltonian cycle, otherwise it should say no, the graph does not have a Hamiltonian cycle. So, the input is a graph, the output is one bit yes or no. Yes if it has this structure, either the path or either the Hamiltonian path or the Hamiltonian cycle, no if it does not. Okay. So, these are the two problems and clearly they seem to be related. I mean, Hamiltonian cycle is a cycle that spans all vertices, Hamiltonian path is a path that spans all vertices. So, one would expect these two problems to be similar in some ways. Okay. In fact, similar, now we have a very clear notion of what similar must be. we want to say something like this, that if you can solve HC, okay, which means if there is an efficient algorithm for HC, there is an efficient algorithm for HP, and if there is an efficient algorithm for HP, there is an efficient algorithm for HC. Okay, so these are the questions we are going to address now. An efficient algorithm for HC, which is the Hamiltonian cycle. Design an efficient algorithm for HP. This is the Hamiltonian part. So how do we do this? So here is my here is an algorithm HC. If I feed in a graph to this algorithm, it will say whether or not it has a Hamiltonian cycle. Okay. Now what I want to design is one for HP. So I want this. Feed in a graph, this should say yes if it has a Hamiltonian path. Okay. So supposing the input is some graph G. I want to determine if this graph has a Hamiltonian path or not, and I have to use this. I have to use this algorithm somehow. Okay, supposing I feed the same graph into HC. Okay, I feed the same graph into HC. Two things can happen. HC can say yes or it can say no. Okay, so let's try this. Let's see what happens in each of these two cases. Okay, I want to determine if G has a Hamiltonian path. Okay, so does G have a HP? This is the question. Okay, so I feed G into HC. There are two cases. This fellow can say yes, and what do you think we can conclude? If it has a Hamiltonian cycle, does it have a Hamiltonian path? Well, absolutely. Yeah. Okay, it must have a Hamiltonian path. So if G says, if this HC says yes for G, you're done. Great. It has HP. Okay, so you can say with surety that if it has a Hamiltonian circuit, it has a Hamiltonian path. You're done. What if it says no? Okay, now we really don't know. Okay, maybe it doesn't have an HP, in which case it doesn't have an HC, and so we're all fine. The problem is the graph could have a Hamiltonian path, but it need not have a Hamiltonian cycle. Okay, so that case we are just not able to distinguish using just a blind way of using this subroutine. So we have to be a little bit smarter in using these subroutines. Okay, and that's the beauty of this subject. You have to figure out how exactly do I use this subroutine HC effectively to get a Hamiltonian path out. Okay, this is what you do. You should maybe try it before you see the solution I'm going to give right now. In fact, this transformation to the graph that I'm going to do, you've seen earlier. Okay, that's a hint. Okay, so what we do is this. So here is G. Okay, I take G as it is. I added, so here's G. Okay, I add a new vertex U. Okay, connect U to everything in G. U is connected to every vertex in G. Okay, now this graph I feed into HC. Okay, I have an original graph where I want to determine if it has a Hamiltonian path or not. I add a vertex, I connect it to every other vertex in G and feed it into HC. Now if HC says, it could say yes or no. So what I'm going to do is, if HC says yes, then I'll also say yes. The graph G has a Hamiltonian path. If it says no, I'll say G does not. Okay, so if HC says yes, then the output of the algorithm for HP will say yes. Okay. If HC says no, I'll say no on this new graph. Okay. However, it's on this new graph. So, does this work? Doesn't this work? Well, it does work. We'll see why. There are two things we have to show. We have to show that if it answers yes, this answer must be correct, which means this graph G must have a Hamiltonian path. Okay. And if it answers no, the graph should not have. So, the two statements that we need to prove is the following, are the following. Here is G, and vertex U is adjacent to every other vertex in G. Okay. So, call this new graph G prime. New graph is G prime. Okay. So, I want to show that G has a HP if and only if G prime has HC. Okay. This is an if and only if statement. So, there are two things. Okay. The two things correspond to yes and no output. Okay. For instance, we have to show that G has an HP. This implies that G prime has a HC. Okay, and the no output G does not have a HP. This implies that G prime does not have an HC. Okay, these are the two things we need to show. So assume that G has an HP. We need to show that G prime has an HC, and I think this should be fairly obvious. So here is G. So here is my HP. I don't know how this looks. Okay, it's a path which runs between, which has all the other vertices in G. Now, I need to construct an HC, which is an Hamiltonian cycle in G prime, and that's easy. I just add these two edges. Okay, so this path starts at some vertex and it ends at some vertex. Okay, it starts at X and ends at Y. The Hamiltonian cycle I get by just appending U to X and Y. Okay, I add the edges Ux and Uy, and I get a cycle in G prime. And you can see that I can go the other way also. So given a Hamiltonian cycle in G prime, I can construct a path, a Hamiltonian path in G, and the construction is similar. So here, supposing this is graph G prime, okay, and I have a Hamiltonian cycle. Okay, it goes around like this in G prime. Now this vertex U sits somewhere. So this is my vertex U. If I remove this vertex U from the graph, what I am left with is a Hamiltonian path in G. Right? Okay, this path will start from this vertex X and will end at this vertex Y. Okay, so the path starts at X, it will go around and end at Y, and this path is in the graph G. Okay, so we have proved the statement both ways, that if the original graph had a Hamiltonian path, the new graph has a Hamiltonian cycle. If the original graph did not have a Hamiltonian path, the new graph will not have a Hamiltonian cycle. Okay, what about the other way around? Okay, we said given an algorithm for Hamiltonian cycle, we could construct one for Hamiltonian path. But what about the other way around? Okay, the other way around would be this: given an algorithm for Hamiltonian path, construct one for HC. Okay, and from now on, if you are given an algorithm, it's efficient, and you want to construct one, that better be efficient. Okay, so these are all. Well, I've just said algorithms. We want efficient algorithms. Okay. The previous one was clearly efficient. I had to call the Hamiltonian cycle routine exactly once. Okay, I do a small modification to the graph. The input size does not go up by much, and I call the Hamiltonian cycle routine exactly once. So the running time is roughly the same. Okay, so the old algorithm was efficient, the new one was efficient. Okay, so how about this? So you're given an algorithm for HP, which means here is HP. So given a graph G, it says yes or no, and what I want is one for HC. Okay, so given, okay, let me call this G prime to distinguish from this G. So this is what you want. Okay, this is what we want. This is given to us. So somehow again I have to use this this routine for HP efficiently to get this routine for Hamiltonian cycle. So how do I do this? I could, let's try the usual trick. I feed this graph into HP and it says yes. If it says yes, then well, it could have a HC or it may not have a Hamiltonian cycle. On the other hand, if it said no, then I'm clear that the graph does not have a Hamiltonian cycle. In fact, does not have a Hamiltonian path. Okay, so yeah, so if it says no, I have no, we're all fine. But if it says yes, again we run into a similar problem. We cannot decide whether it has a Hamiltonian circuit or not. Okay, so what do we do? So here is an attempt. Take the graph G. Okay, so I want to use, let me just put this on the side. Okay, this is what I want to use, and I want to create one for HC. Okay, so what do I feed into HP? So take this graph, this input graph G. So take G. Now remove edges from G one by one. Okay, so let's say I remove some edge E. Now I feed it into G prime and I'll see whether it says yes or no. Okay, now if it says no for any edge, then clearly the graph will not have a Hamiltonian cycle. Okay, why is this? So supposing G has a Hamiltonian cycle, then if I remove any edge from G, the graph still has a Hamiltonian path. Okay, so if I take G and remove any edge, the Hamiltonian path must keep saying yes. Okay, is this a good algorithm? I mean, can I sort of say that you remove every edge from G, feed it into HP? If it says yes all the time, then yes, G has a Hamiltonian cycle. If at least once it says no, then G does not have Hamiltonian cycle. Okay, let me write this algorithm now. For each edge, E, call HP with G minus E. Okay, if HP says yes for all edges, then G has an HC, so you output yes. Okay, otherwise output no. So if it says, if HC says no for any input, okay, then you say no. So this is the algorithm, and well, the question is, does this work? What do we mean by this question? I mean, what does it mean for this to work or not? It means that whenever you output yes, okay, whenever you output yes, the graph better have a Hamiltonian cycle, and whenever you output no, the graph should not have a Hamiltonian cycle. Let's take both of these in turn and see whether we can prove this. Okay, so let's take no first, because that's easier. So you output no, so we output no if for some edge E prime, okay, G minus E prime does not have a Hamiltonian path. So if I remove this edge E prime, then the graph does not have a Hamiltonian path. Okay, we've seen that this implies that G does not have Hamiltonian cycle, because if it had a Hamiltonian cycle, then if I removed any edge out, I would still have a Hamiltonian path in the resultant graph. So whenever we output no, we are in the clear. Okay, we are correct. The algorithm is always correct. What about the yes case? It seems very reasonable that for every edge, if I remove it, okay, and ask whether it's a Hamiltonian, there's a Hamiltonian path, and it says yes, it seems reasonable that there should be a Hamiltonian cycle. So if there is a Hamiltonian path after removal of any edge, there's a good chance that one feels that the graph should have a Hamiltonian cycle, but this is false. Okay, so this statement is false. Let's see an example. Okay, so here is an example. Okay, so this is an example of a graph so that after removal of any edge, the graph has a Hamiltonian path, but the graph does not have a Hamiltonian cycle. Okay. So there are two things to be checked with this graph, that it does not have a Hamiltonian cycle, but if I remove any edge from this graph, any edge at all, then this graph must have a Hamiltonian path. Okay, let's check both of them. Now this graph does not have a Hamiltonian cycle, and to see that, you focus on this vertex in the middle. If I remove this vertex, okay, then the graph becomes disconnected. There is a vertex in this graph, so that if I remove this middle vertex, then the graph becomes disconnected. Okay, this cannot happen if the graph has a Hamiltonian cycle. If the graph has a Hamiltonian cycle, if I remove any vertex, the resultant graph will have a Hamiltonian path and will in fact be connected, right? So if a graph has a Hamiltonian cycle, if I remove any vertex, it must remain connected. That is not true for this graph. Okay, so that's the reason this does not have a Hamiltonian cycle. We still have to prove one more thing, okay, which is that if I remove any of these edges in this graph, then it should not have, it must have a Hamiltonian path. Okay, so let's look at these edges one by one. So let me draw this graph again. So let's focus on this edge. Supposing I remove this edge, does there exist a Hamiltonian path? Well, the answer is yes. Okay, so choose this edge, choose that edge, choose this edge. Okay, you come down this way. Then you choose this edge. Okay, go down this way. Choose this edge and that edge. There are other ways of doing this. Okay, so you go up and down like this, and this you can see is a Hamiltonian path. So removal of this edge here causes no problem. Okay, so let's look at some other edges. Okay, so let's remove this edge. What if I remove this edge? So in this case, okay, I can start here. Okay, come down here, go up here, there. Let's say this and this. Okay, this will give you a Hamiltonian path. So you start here, you go up and down like this. Okay, go up, go down, and up to this. And this you can see gives you a Hamiltonian path. So removal of this edge is also not a problem. So let's look at one more. Okay, so let's remove this edge. If I remove this edge, okay, the graph still has a Hamiltonian path. This. Okay, so you go down this way, go back, or go down, keep going down, go up all the way up here, go down and back here. So if I remove this edge too, there is a Hamiltonian path. Now we just see that all edges in the graph are similar to one of these three. Okay, for instance, this edge is similar to that, right? This edge at the bottom is similar to this, right? So all edges on this side is taken care of. These two edges are taken care of. This is the middle edge. These two are similar, and the graph is symmetric about this vertex. Okay, so all edges on this side, on the left-hand side of the graph, are also taken care of. So these three cases are enough to enumerate to sort of convince, hopefully convince you that removal of any edge in this graph leaves the graph with a Hamiltonian path. So this the algorithm that we described is wrong. This fails. Okay, so it looked like a very reasonable thing to try, but it fails. So what you do is this. So here's my graph, right? So here is, let me take some edge UV. Now what I'll do is remove the edge UV, okay, remove this edge, and I'll attach two other vertices. Okay, this is U prime and that's V prime. Okay, so I have an original graph G, I remove the edge UV, okay, that's gone from here, and then I attach two additional vertices U prime and V prime. Okay, now I ask if, does this graph have HP? Does this graph have a Hamiltonian path? The question we wanted to answer was, does this have a Hamiltonian circuit? Okay, now let's see. Supposing this graph did have a Hamiltonian circuit. Okay, supposing this had a Hamiltonian circuit, not only that, the Hamiltonian circuit passed through the vertices U and V in order, okay, which means the edge UV was present in some Hamiltonian cycle in the graph. Then let's notice that this new graph has a Hamiltonian path. So what does it mean for this graph to have a Hamiltonian cycle passing through UV? It means there must be a cycle this way, okay. It goes through all other vertices and also includes UV. So let's look at the same cycle. So I take the same cycle and I add these two edges and I get a Hamiltonian path in the new graph. So if the old graph had a Hamiltonian circuit, okay, then if I picked an edge which was present in the Hamiltonian cycle and asked if this has a Hamiltonian path, then it will have a Hamiltonian path. Okay, that's the first thing to notice. Now here's the second thing to notice. Okay, supposing I took a graph like this. Okay, so I took a graph and so here is G, I took a graph G, edge UV, okay, I removed UV, attached U prime and V prime, and I ask if this has a Hamiltonian path. Supposing this says yes, what does the Hamiltonian path look like? Now the path has to, these two vertices have degree 1, so they have to be the end points of the path, okay. U prime and V prime have to be the end points of a Hamiltonian path, which means the Hamiltonian path has to look like this. It has to start at U prime, then go through all vertices in G, okay, and then go back up to V prime. This is how the Hamiltonian path should look like. Then what you could do is this, remove these two edges, okay, and put this edge UV which you had removed back in. This will give you a Hamiltonian circuit in the original graph. Okay, now our algorithm is almost complete. Okay, what we do is we do this for all edges in the graph. We remove that edge, attach this U prime V prime, okay, and ask if it has a Hamiltonian path. If for any edge it says yes, then we say great, this has a Hamiltonian cycle. If for all edges it says no, then we say no, it doesn't have a Hamiltonian cycle. Okay, so let me write this algorithm, then we'll argue that this algorithm is in fact correct. Okay, so the algorithm is this: for every edge E, okay, do the following. So remove E from G. Okay, let's say E is okay, say E equals is UV. Okay, then add vertices U prime and V prime and connect U prime to U and V prime to V. Okay, this, let's say, gives graph G, let's say E. Okay, for an edge E, I get this graph GE. Now feed GE, that means input GE to an algorithm for HP. Okay, if this algorithm says yes for any E, output yes. If it says no for all E, you output no. Okay, so otherwise output no. So you output no if it says no for all edges. For all edges, you do this: you remove the edge, add these two extra vertices, and ask whether it has a Hamiltonian path. If it says no for all these edges, then you output no. Okay, this is the algorithm, and we have to show that this is correct, which means if the original graph had a Hamiltonian circuit, right, then this algorithm will always say yes. If the original graph did not have a Hamiltonian circuit, it will say no, and it's efficient. Okay, if the Hamiltonian path algorithm ran time polynomial in the input size, so does the new algorithm. Okay, these are the three things to check. Let's just make sure that the algorithm is efficient first. Okay, you call it once per edge, right? The Hamiltonian path routine is called once per edge, and you do not change the input size by much. You just remove one edge and you add two more edges. So the number of edges goes up by one. So the input size does not go up by much, and you're calling it at most m times. Okay, so if the original running time were bounded by some n to the constant, it is still bounded by n to some other constant. Again, there are two cases. Case one is when the algorithm outputs yes, then it has to be correct. The second case is the algorithm outputs no, this no answer also has to be correct. Okay, let's take both these cases. So case one, so the algorithm outputs yes. So this implies, okay, that means for some edge, HP must output yes. Okay, this means there exists an edge E in G such that GE has Hamiltonian path. Okay, so here was G and here is E. I get GE by removing E and adding these two. So this had a Hamiltonian path. And now we have seen this argument that if this has a Hamiltonian path, then this has a Hamiltonian cycle. Essentially, you take the Hamiltonian path here, remove these two edges, okay, and add this edge back to get a Hamiltonian cycle here. So this case is done. The algorithm outputs no. Okay. This means for every edge E, okay, GE does not have a Hamiltonian path. Okay. So we need to see that this implies that G does not have a Hamiltonian circuit. Okay. So this is what we need to show. So we need to show that for every edge E, if G does not have a Hamiltonian path, then G does not have a Hamiltonian circuit, right? Now it's easier to prove the contrapositive, okay, which means this statement which I have written is equivalent to saying the following, that, okay, this, let me write the equivalent statement on the right hand side. So I'm going to say that G has a Hamiltonian cycle. This implies, okay, if G has a Hamiltonian cycle, what should happen? This means this statement cannot happen, okay. It is not the case that for every edge E, G does not have a Hamiltonian, which means there exists an edge E such that GE does not have a HP. So these two things are the same, okay. So these two are equivalent. Okay. So let me sort of just say what I'm doing. So you want to prove that A implies B. You're proving that not B implies not A. Okay. I want to prove that this implies this is A and this is B. So I want to prove that A implies B. All I'm doing is not B is this, implies not A, which is this. Okay. So I'm going to prove that if G has a Hamiltonian cycle, there exists an edge such that G does not have a Hamiltonian path. And you can see this also we have proved. If G has a Hamiltonian cycle, okay, that's G, okay, that's my Hamiltonian cycle. If I remove any edge in the Hamiltonian cycle, okay, so if I remove this edge and I attach these two vertices, this resultant graph has a Hamiltonian path, which is what we wanted to prove. So we want to prove that G has a Hamiltonian cycle, there exists an edge such that G does not have, G does have a Hamiltonian path. I'm sorry about this, okay. G does have a Hamiltonian path, and this we have just proved. In fact, this edge E can be any edge in the Hamiltonian cycle. So remove any edge in the Hamiltonian cycle, okay, that for that edge, removal of that edge, GE will have, if you remove that edge and attach those two vertices, this new graph GE will have a Hamiltonian path. Okay, so when we looked at these problems, there were two kinds of problems we looked at, okay. For some problems we said, we wrote input, output, okay. For certain other problems we said input, question. Okay. Now when I looked at problems like like finding a matching of maximum weight or finding a matching with maximum number of edges, they were of the form input and output, because the output was edges which were there in a matching of maximum size, right. Now for instance, does the graph have a Hamiltonian cycle? That's the question. The input is a graph. Does the graph have a Hamiltonian cycle? I ask a question. The answer should be yes or no. Now the difference was for these kinds of problems, the answer was a single bit. It was yes or no. For these problems, the output spanned many bits. So these had a single bit as output. These could have had many bits as output. For instance, edges in a matching. In fact, let's look at the Hamiltonian cycle problem. Okay, we said input is a graph G, does G have a Hamiltonian cycle? It's yes or no. Okay, the answer is yes or no. On the other hand, I could have asked for an output saying output a Hamiltonian cycle. Input is a graph G, output a Hamiltonian cycle. Now this problem seems to be somewhat similar to the previous problem. Only here the output has many bits. You have to output every edge in a Hamiltonian cycle. Okay, you have to choose one Hamiltonian cycle and output the edges from this Hamiltonian cycle. So we would like to distinguish between problems where we require the output to be one bit and problems where we require the output to be many bits. These we call decision problems, and these we call search problems. Okay. So typically here for decision problems, so let me write decision and search. So here output is one bit, here is many bits. So here you want to decide whether true or false. Here you want to search for a solution and output the solution. Okay, that's why this, I guess that's why these are called decision and these are called search problems. So example, so here does G have a Hamiltonian cycle? Okay, so this is an example of a decision problem, example of a search problem, output a Hamiltonian cycle if one exists. The input is the same to both, which is a graph G. In one case, you just want to know whether G has a Hamiltonian cycle or not. The other case, you want a Hamiltonian cycle output. You want actually the edges in the Hamiltonian cycle. Okay. Now, how do these two problems relate to each other? Is one easier than the other? Is one harder than the other? Now, it turns out, okay, people have just observed it, that they are related to each other quite closely, in the sense that if one is easy, the other one is easy. If one is hard, the other one also turns out to be hard. Okay, so let's take this Hamiltonian cycle problem and see this. Okay, so I have so the input is a graph G. Okay, now there are two problems. One is does G have a Hamiltonian cycle? Okay, this is one. And the second thing, output a Hamiltonian cycle if one exists. So this is problem 2. Okay, that's problem 1. Now, supposing there is an algorithm for problem 2, okay, so which means given if you feed in an input graph, the subroutine outputs a Hamiltonian cycle. Can we find an algorithm for problem 1? Okay, yes. I hope all of you answered yes. Okay, so the answer has to be yes. So you just feed the graph in, okay, to this subroutine, and you look at the edges which have been output. So if it forms a Hamiltonian cycle, then you just output saying that yes, it does in fact have a Hamiltonian cycle. So that's trivial. And if it says no, it does not, the original routine says no, it doesn't have a Hamiltonian cycle, I cannot output these edges, then you just output saying no. Okay, so that's trivial. Our job is to look at the other way, the problem the other way, which means I have an algorithm for problem 1. Okay, so I have an algorithm for this. Now I want an algorithm for this. So given well, let me add efficient just to remind you that we are talking of efficient algorithms. Given an efficient algorithm for problem 1, okay, construct one for problem 2. Okay, this is what we really want to do. And how do we do this? We have actually done something like this before, which was with respect to matchings, right? When we wanted to find the edges in a matching of maximum weight, we used a subroutine which answered something else, right? And we somehow got these edges out. And we'll use absolutely the same trick here. Okay. So what we do is this: we look at the edges one by one. Okay, let's say the edges are E1, E2, E3, E4, and so on. Okay, so you look at the edges one by one. I remove E1. Now I ask if the graph has a Hamiltonian cycle or not. If the graph has a Hamiltonian cycle, it has a Hamiltonian cycle which does not use this edge E1, so I just throw away E1. Okay. Similarly, I look at E2, I remove E2 and I ask if the graph has a Hamiltonian cycle. If it says, if the subroutine says yes, I just throw away this edge and I keep doing this. Supposing I remove an edge and it says the graph does not have a Hamiltonian cycle, then you also know that this Hamiltonian cycle uses this edge, right? So these edges you put back in. You do not want to throw these edges away. So you just do this. Look at all edges one by one. For those edges where the algorithm says that it does not have a Hamiltonian cycle, you throw away those edges. For the edges for which the algorithm says that there is, I mean, if you remove, there is a Hamiltonian cycle, you throw away those edges. For edges where when you remove the edge and ask the question, it says that no, there is no Hamiltonian cycle, that means this edge must be present, you put it back in. Okay. So you do this for all edges, and at the end of it, you've thrown away some edges and some edges remain. The claim is the edges that remain must form a Hamiltonian cycle. Okay. Firstly, the graph must have a Hamiltonian cycle, because whatever remains, whenever we asked whether it has a Hamiltonian cycle, it said yes. Okay. So the graph that remains must have a Hamiltonian cycle. Why should there not be other, spurious edges floating around? Why should it not have, apart from the Hamiltonian cycle, other edges? Supposing it had some other edge. When you removed this edge and asked whether the graph has a Hamiltonian cycle, the answer should have been yes. So if the answer is yes, you would have thrown this edge away. Okay. So there are no spurious edges. The only edges which are present are Hamiltonian cycle edges. Okay. So let me just write this. So just to recap, we are given an algorithm that says whether a graph has a Hamiltonian cycle or not. We are constructing, using this as a subroutine, we are trying to find out edges in some Hamiltonian cycle. Okay. So consider the edges one by one. Okay. For edge EI, remove EI and ask HC if the resultant graph has a Hamiltonian cycle. If it says yes, throw away EI, else retain EI. Okay, that's it. You just do it for all edges. Finally, what remains is a Hamiltonian cycle, which means what remains are edges from a Hamiltonian cycle. Okay, so you can see that both problems are quite related. I just need to call the other algorithm m times to able to actually extract a Hamiltonian cycle out of it. So it's been observed that for most problems, okay, there are of course problems which do not fall into this, which do not have this property, but for most problems, if I can sort of decide, okay, then I can also search for a solution. So if the decision version of a problem is easy, then even the search version is easy. Okay. On the other hand, if the search version is hard, then so is the decision version. Okay. Yeah. So this is the reason we are going to focus on decision versions of problems from now on. Okay. So we are just going to look at problems and decide problems whose output is 1 bit, and say yes or no. We are now ready to define the class NP. Okay, so before I formally define this, let me sort of give you an informal definition. Okay. Let's take our favorite Hamiltonian cycle problem. So HC, the input is a graph G, and the question is, does G have Hamiltonian cycle? Okay, let's look at this problem. Just consider this problem. Okay, now we are going to do something slightly different, okay, from what we have been doing. We are not going to design algorithms for the time being. What we are going to do is have a game between two players. Okay, there are two players now. Okay, one I'll call a prover, and one I'll call a verifier. Okay, these are two people, prover and verifier. Prover is all powerful. Okay, he just knows everything. Yeah, the verifier has limited resources, and he doesn't trust anybody. Okay, he sort of doesn't trust. Especially he doesn't trust the prover. Okay, he has limited resources. Now the prover and verifier are sort of sitting, let's say in a room, and there's a huge graph in front of them. Okay, just imagine there is somebody has drawn a huge graph in front of them. The prover looks at the graph and he says, this graph has a Hamiltonian cycle. Okay, so he's all powerful, he can figure these things out. Okay, and he says this graph has a Hamiltonian cycle. Now the verifier, he is skeptical, he doesn't believe the prover. So he says, why should the graph have a Hamiltonian cycle, and what's the deal? Then what should the prover do? The prover wants to convince the verifier that, you know, he's all powerful and he has made the right statement. He said the graph has a Hamiltonian cycle, and the graph has a Hamiltonian cycle. So he wants to convince the verifier that the graph has a Hamiltonian cycle. So what could he do? Well, if you think about this for a minute, what the prover could do was pick out the edges from the graph which form some edges which form some Hamiltonian cycle. Okay, so pick out some Hamiltonian cycle from the graph and tell the verifier that here are a set of edges which form a Hamiltonian cycle. Now all the verifier needs to do is look at these edges, make sure that they form it, and make sure that they form one big cycle. Right? He just has to verify that these set of edges form a Hamiltonian cycle, which is easy to verify. Okay, even though he has limited resources and he is not too intelligent, this much he can do. So this prover has somehow convinced the verifier that this graph has a Hamiltonian cycle. So the prover says that there is a Hamiltonian cycle in this graph. The verifier asks why. The prover then picks out the edges. He says these are the edges. Look at these edges, they form a Hamiltonian cycle in the graph. The verifier then verifies that yes, indeed the graph did have a Hamiltonian cycle. Okay. And we have just proved, okay, that Hamiltonian cycle is in the class NP. I have not defined the class NP. Okay, so you really don't know what it is, but this is all there is to proving that problems are in the class NP. Okay, so let's do this prover verifier game for some other problems, just to get sort of just to get used to it. Let's say the input is an integer t. So you want, so the output factors, let's say two non-trivial integers t1 and t2 such that t equals t1 times t2. So you want to find factors of these. Okay. Now this is a search question, it's not a decision question. So the corresponding decision question is the following. So here is a question. Okay, is T composite? Which means can T be written as T1 times T2, where T1 is not 1 and T2 is not 1. Okay. So these two are non-trivial factors of T. Let's play the same prover verifier game. Okay. So here is the prover, whom I'll say is P, and here's the verifier V. So P says T is composite. Okay, he says. Now V asks why. Now P has to convince V that in fact it is composite. So prover sends T1 and T2 across. Okay. So once he sends T1 and T2 across, V multiplies T1 and T2 and checks the result with T. So if it's equal to T, then of course he is convinced that T is composite, and in fact T1 and T2 are two factors. Go back and look at this Hamiltonian cycle problem again. Okay, so let's look at this again. Now if the answer was yes, I mean it does have a Hamiltonian cycle, okay, which means the prover said it has a Hamiltonian cycle, then the prover could convince the verifier that the graph does have a Hamiltonian cycle. What if the prover says no, it doesn't have a Hamiltonian cycle? Okay. So yeah, so initially he says yes. Okay, so this guy asks why. So he sends edges in HC. Okay, and this guy verifies. Now supposing he says no, it does not have a Hamiltonian cycle. Now the verifier asks why, and well, what does the prover do? How can he convince this verifier a given graph does not have a Hamiltonian cycle? Now think about this for a little while, you will see that it's a difficult question to answer. How can you convince somebody that this graph does not have a Hamiltonian cycle? Well, the only way seems to be that you just try all possible subsets of edges of whether they form a Hamiltonian cycle or not. If none of them form, then it doesn't have. But this is a brute force method, and the verifier does not have so much time. Okay, he doesn't have so much time to check all possible subsets of edges. So there is no easy way for the prover to sort of convince the verifier that G does not have a Hamiltonian cycle. Okay, so it looks like the answer to the question, whether it's yes or no. If it's yes, the prover can convince the verifier. If it's no, the prover is not able to convince the verifier. Okay, so they behave sort of differently.